Coming out. And let's go ahead and get speakers underway. We have some great speakers today. And our first speaker, we're really excited. There's a really vibrant and growing cosmology group at Duke University. Who knew that already? Okay, so now you know, and you're going to get to hear about some of the work that's getting done down there. If you were here last fall, you saw another of the speakers from that group. Dan Skolnick was here to give the Joe Klein Memorial Lecture. But just this past year, they hired a new cosmologist, Vavagiakis, who is sort of an experimentalist kind of person. She likes building equipment, and she's involved with some of the observatories down in Chile. And so she's going to tell us today about what she does. So let me turn things over to her and enjoy.
Thank you. Let's see. I'm loud enough here. Can everybody hear me? Do I need to put the?
Is that? You
can put that on.
Because we're going to try to record them.
Okay. Yes. Okay. Great. All right.
This thing has a laser pointer if you don't have that.
Okay, audio test. Sound good?
Can y'all hear?
Can
audio?
I? Let's see. Is it on? It might not be on.
It may not be on.
There we go.
Okay.
Okay, test now. Better? All right, excellent. Put this into presentation mode. Okay, hello everybody. My name is Eve. It's a pleasure to be here. I have not been to Greensboro yet. I just moved to North Carolina in July to start at Duke. So this is my first year down here, and all of the people have been incredibly welcoming and friendly, so it's been a great joy. So thank you for having me in your state. And today I'm going to be telling you about some experiments that I'm bringing to the Duke Cosmology Department. Previously, there have been experts in optical surveys and in novel analysis approaches and simulations work, but there has not been hands-on laboratory physics at Duke in the field of cosmology, and so I'm very excited to bring that to the field. So here is my cover slide to kind of excite you by overwhelm. You can see what the sky might look like in a very exaggerated form if you were to have millimeter wavelength eyes. And then you see some telescopes and cameras that I'll tell you about today, much bigger than in real life, all set in front of a picture of a real observation site that I'll talk about in one of the driest observation locations on planet Earth in the northern Atacama Desert of Chile. So I'm excited about cosmology because it's intellectually greedy, I like to call it. We get to look at the biggest questions possible and study all of space at once. I started college being very excited about space science and astronomy, but had a very hard time picking what exactly I wanted to look at or study, and cosmology allowed me to kind of do it all, so to speak. So cosmology is the study of the universe as one single system. We don't necessarily look at individual astronomical objects. However, our surveys enable us to do that, and so we do astronomy and astrophysics as well. But cosmology gets to answer, or try to answer, some of these questions that we've asked since caveman days, looking up in the night sky and wondering, what is all of this stuff? Where did we come from? Where are we going? What the heck is going on? And now we're still sitting in our labs and scratching our head and answering some of these questions with the use of these large novel instruments, which I'm excited to be a part of building. So the Astro 2020 Decadal Survey kind of sets the stage for funding priorities for federal funding and other types of funding efforts, now maybe more important than ever. And in the Decadal Survey from 2020, it was noted that this explosion of high-resolution cosmic microwave background data is opening some frontiers that have previously not been accessible to us. So it's only by building new telescopes and new instruments and improving the resolution and sensitivity of our data sets at millimeter wavelengths that we're able to start studying some of these tiny little signals that we weren't able to measure before. Here, CMB stands for Cosmic Microwave Background. I'll be using that acronym a lot. This is the oldest light accessible to us. It's the remnants of the Big Bang as you look back out in redshift as far as you can possibly look. It's when the universe became thin enough for photons to first travel. So here is another kind of excite by overwhelm slide showing some of the technology development that goes into making these novel measurements. We pick the most extreme environments on Earth to get us as close to these signals and away from our atmosphere that would otherwise contaminate or absorb our measurements as possible. So here we're looking at the Atacama Desert. There are also sites that are excellent down in the South Pole. My work hasn't been too involved in the South Pole, so I'm going to focus on the Atacama. There's also a high site in Tibet that people are working towards, which is exciting as well. And then up here, you're seeing, I can use this laser pointer. Yeah. This is a baffle that reduces ground pickup for the telescope. And you're going to see it a lot in some more photos. This was the Atacama Cosmology Telescope. It's on my T-shirt. And you actually can't see the telescope at all. It's just the fore baffle. So here are some detectors that we are developing, and I'm mounting some portions of the detectors for testing there. This is me in grad school. And then here are some of my colleagues putting together the guts of the camera that goes inside of this telescope. And so it's only through advancing technology that we're able to do these measurements. And now today we're pushing this further. Our detectors are actually background limited, which means that we cannot do any better in terms of the detectors. We can only field more of them to have more sensitive measurements. So we're working on that by building these enormous cameras that you're going to see more of to field larger and larger quantities of these detectors. And then here you can just see some of the beautiful images that we can use in concert with one another in order to kind of fill in the spectrum beyond the millimeter and submillimeter wavelengths in which we're observing to look at optical surveys that trace out galaxies far back into time and to observe astronomical objects that are interesting and overlap in frequencies in ways that we can eke out frequency-dependent signatures and physics that you couldn't access in one band alone. So here you can just see kind of an evocative, fiery Milky Way arm that kind of stretches through our maps as we observe the cosmic microwave background. Signals like this are both contaminants, getting in the way of fundamental cosmology measurements, and also very interesting to study in their own right. So new telescopes being built are going to be looking at the signature of the Milky Way and trying to understand both our home galaxy as well as the universe as a whole. So today I'll talk a little bit more about ground-based observations of the cosmic microwave background. I will talk about measurements with ACT and talk to you about the Sinayev-Zildovich effects. How many of you have heard that before? Okay, a couple, great. Hopefully, user-friendly overview of this interesting signal. And then I'll be talking about some new telescopes that have literally just turned on. The Simons Observatory's Large Aperture Telescope saw first light last week. So this is happening very, very much right now, which is very exciting. And CCAT is literally on a ship. It just passed through the Panama Canal. So it's an exciting time for this. Okay, so what can we learn about the universe by studying this ancient light? I'm excited for this drone footage that I got access to literally 2 days ago. So why don't we enjoy the Atacama Desert here for a moment. That's ACT there. So ACT no longer exists, actually. This doesn't look like this anymore. ACT was decommissioned in 2022. Now the ground screen here, this is now the actual telescope. You can see the 6-meter mirror right here. The ground screen is being used as a ground screen for a different telescope for the Simons Observatory, but this is what it looked like back in the day. That's the camera. And the Atacama Desert is this really incredible extreme environment. When you work here, you can get sunburned through your clothes. The highest UV index ever recorded was on a mountain right next to the mountain that ACT observed on. Does anybody know what the highest UV index ever recorded on Earth is? I forgot if it's one number or another, but I'll tell you what the ballpark is. But does anybody know? Yes, probably. But it was on this nearby stratovolcano to this observation region, and it was either 47 or 49. But if you know UV index, you look at your phone, like 10 is like you need to cover up. So 47 is just kind of unthinkable. So it's an extreme environment. It's very dry. It gives us access to frequencies that we enjoy really great clarity in which the Earth's atmosphere is not absorbing the light. So we observe in a number of bands spanning between 30 and 220 gigahertz. This gives us access to the peak wavelengths of the cosmic microwave background. And so, again, not here anymore. Now it's in some museum has agreed to take it. I don't know what the status is of the telescope itself now, but observed for many years. between 2008 and 2022. And the 6-meter aperture mirror gave us access to high-resolution maps at 150 gigahertz. It's 1.4 arc minutes in resolution. And that's not high resolution for optical images, right? But that is really good for the CMB. And I'll show you some pictures of why that's helpful later. And yeah, I'll note the high elevation here. That's 5,200 meters is a little over 17,000 feet. So when we work up there, we have to wear oxygen, and you get a headache pretty easily. This is just a picture of our collaboration. I think this was our last collaboration meeting in 2022. It was like yesterday. We were signing. This is actually not a mirror panel that came off of the mirror, but it kind of looks like that, so I like using this. This is actually a reject. It was never used. But we still used it to sign and kind of wish ACT well. But we have been working in the years since to continue to use ACT data because the data keeps coming out. And if you yourself are interested in looking at the maps from ACT, you can do so. You can go onto the NASA Lambda server and open up some of these FITS files and view the images and kind of scroll around, see what you can find, or use them for your own scientific analysis like we're doing. So that's still going, and I'll tell you a little bit about some of the science I'm working on with ACT data in a little bit. Okay, so CMB basics. This is actually an image that an artist illustrated from my children's books on neutrino physics. I have a series of, it's called Meet the Universe children's books about different astronomical and particle objects, and photons is going to come out in May, which I'm excited about. But here you can see these little sneaky neutrino characters that are not to scale, kind of flying around the universe. Those are coming from the cosmic neutrino background, which we won't talk about today. But what we are talking about is the cosmic microwave background, which is denoted here. So at the very beginning of the universe, we had this very hot and dense plasma. And it was only once the universe expanded enough so that photons didn't just ricochet off between particles, but indeed began to free stream through our universe, that we're able to detect that light today. That happened about 380,000 years after the Big Bang. And so once the photons were released and began to free stream, they traveled through our universe and eventually hit our telescope here, again, not to scale, on Earth today after their 13.8 billion year journey. And we're interested in studying the cosmic microwave background because it's basically a baby picture of the universe. And you'll see this word kind of throughout the slide, primary anisotropies. What does that mean? Well, the cosmic microwave background really doesn't look like this. If you are familiar with the history of its observation, Penzias and Wilson in New Jersey discovered the cosmic microwave background radiation when working on a different telescope that was definitely not, it was some kind of an antenna situation that they thought this was noise that was an issue with their instrument. They actually were concerned it was pigeon poop. They're trying to clean the thing off and try to understand what is the signal that I look in any direction here and I'm getting this noisy pickup. That is the cosmic microwave background. It's highly isotropic or even in black body radiation, no matter where you point on the sky. So it's easy to assume it was some kind of a systematic issue where you look over here, it's the same signal, you look over there, it's the same signal, it might just be something wrong with your instrument. But no, it's a real signature, and it is highly uniform across the sky. It's a black body radiation at about 2.7 Kelvin. But when you zoom in and increase your resolution to this tiny, 1 part in 100,000 level, you start to see these little fluctuations around that even number. And those fluctuations we call anisotropies. And primary anisotropies are the anisotropies caused by the very early universe. I'll talk about secondary in a little bit. But primary anisotropies were encoded at that 380,000 year level in the universe's history. And so we're interested in learning about the fundamental primordial nature of our universe. And we can do so by doing a mathematical deconstruction of the signature in the light. So, well, this one, yes. Yeah, this I was going to say. This one is a Planck map that was at microkelvin levels. So we're looking at probably a scale of -100 to 100 microkelvin here. And so what we do is we take that picture. So we use our telescopes to observe the light. We do so by taking a wide field survey from the ground. From Planck, you get the whole sky. We get a portion that's about a little over 40% of the sky, like in this region from Chile. We take this map, we get the best image we can possibly get, and then we do this deconstruction into Fourier modes here, which I have a GIF here, which tells you what the power spectrum of the light is. The power spectrum is just telling you what the intensity is at a given angular scale. So for example, low L are these large angular scales in the sky. That's down here. And then high L are the tiny modes. That's what we can get to by increasing the resolution of our images. And so this GIF is trying to give you some intuition where the CMB would look kind of dim when you're just looking at these big scales. But you notice a peak at about degree angular scales. And your eyes are kind of just doing that for you. Your brain, when you look at this, is naturally noticing that the fluctuation is kind of degree-ish. Right? You look at this and you see the pattern at a certain typical scale. That corresponds to the peak of your measurement. But essentially what this does, once we have a mathematical signature of the power spectrum of the light, is that we can also write down a mathematical model of the physics of our universe. And then we can constrain that universe physics by observing the CMB and measuring its power spectrum. So this is a little bit of a complicated image. I'm trying to give you the nuts and bolts of some of these things that you might see in journal articles in the archive. This is the power spectrum in temperature up on top as measured by a number of experiments, including ACT. And you can notice that the uncertainties are very, very small. The error bars practically disappear because we've measured this so well. It's only when we go down into polarization that we start to see these large uncertainties. And this is kind of the next frontier. We're trying to measure this better and better. And the signatures in polarization are interesting because they target some of these open questions in cosmology, such as, was there this period of early universe expansion? If there was, and it was big enough, we could measure it down here, but this is already an exaggerated case, and you can imagine how much smaller it might be if this number was smaller. So it's just a tiny little bump down here. We really need to push in terms of our abilities to possibly constrain signatures like that. But what we have done is we've checked each other's measurements. All these experiments are in great agreement with one another. And we've looked at measuring this power spectrum from the ground and comparing it to what satellites see. And the cosmology community, in terms of CMB physics, is in agreement. We have this lambda CDM model of cosmology, lambda being dark energy, CDM being cold dark matter that clumps down into the structures we observe today. And we have a cosmology, a kind of standard model of physics that describes our universe with excellent agreement with one another. Now we have some open questions about that, especially with other colleagues of mine at Duke, like Dan Skolnick, which Tom mentioned, who are looking at the physics of our universe from late time probes. That would be galaxies that formed sometime here, rather than looking at this epoch of our universe. And we do see some disagreements, some tensions, like the Hubble tension, which I'll talk about in a little bit. So there's interesting nuggets of potential avenues for new physics that we're also trying to go down. But the cosmology field, from the CMB perspective, is in great agreement with one another. So the Hubble tension is this interesting situation we find ourselves in that is very timely. So a few decades ago, there was no Hubble tension because our uncertainties of the various measurement approaches were large enough that they were all in agreement with one another. What is the Hubble tension? Well, H naught is the Hubble parameter that parametrizes the expansion rate of the universe. This tells us how fast objects are moving away from us in the universe relative to us. And you can measure this in a number of different ways. One of those ways depends on the CMB, like I've been talking about. And this does depend on the assumption of a cosmological model. That means that squiggly power spectrum that I plotted previously, that is an assumed model. You need something to fit to in order to get your measurement of the Hubble parameter. Type 1a supernovae measurements don't depend on this model. And it turns out that there are differences in the answer you get for H naught when you measure them from the CMB and from type 1a supernovae. You can see that down here. So local measurements are referring to later time probes, like type 1a supernovae, that are giving you a higher H naught value than the CMB world. And so you can see these bands of color here. Those are kind of averaging CMB land and type 1a supernovae land. And we are now seeing a tension, which depending on your data set that you're looking at is above 5 sigma, which is the gold standard of some kind of a significant difference. And this is really exciting because these types of tensions are where new physics lies and where we might be able to make the next big discovery. So it's pretty exciting. And it's also only a result of decreasing these error bars. Like I mentioned, if they're big enough, you're just in agreement, you can't ever find these tensions. Okay, there's a wealth of primary anisotropy information to get to, but my research is mainly in secondary anisotropy land, and that also has all the cool astrophysics to it. So I'm going to switch gears and go into secondary anisotropies now. So anisotropies, again, still refer to little fluctuations in the cosmic microwave background, but instead of being encoded at that 380,000 year period, they are encoded in later time. So they imprint information about the evolving universe. And you can look at objects like galaxy clusters, like I do, by studying secondary anisotropies. I like using this diagram because it kind of gives you a sense of space. I think when you look out in time, you're looking back through stuff. Indeed, you're looking through a lot of stuff. All of the galaxies, the clusters, the large-scale structure in our universe is lying between us and this cosmic microwave background, because it is indeed a background. And you can do a lot of really neat stuff. I'm just going to flash up some really impressive pictures from ACT to hopefully get you excited about this. One thing that is a secondary anisotropy that is, I think, very interesting is this property of gravitational lensing. Have you all seen the Einstein rings that form? Yeah. So it's kind of like that, but it's less impressive just in individual pictures. It's a slight distortion of the light because of large-scale structure across the whole sky. So what you can do, actually, is map out all of the gravitational potentials in the sky by looking at how the cosmic microwave background is distorted as it moves through all of that structure. So you can see up in the upper right-hand corner here, CMB photons naturally have to traverse a very complex gravitational potential field before they reach us on Earth. And what ACT has done is enabled us to map out almost 10,000 square degrees of sky in terms of lensing mass. And we know that baryonic or normal matter is making up a minority of our universe's composition. Indeed, most of the matter in the universe is dark matter, which we don't know the nature of. And so this mass distribution is essentially a dark matter map. We are mapping out dark matter across a large part of the sky. And here in these colors, you see peaks in orange and voids in purple. And what you can do with this is, again, look at the interesting parameters inside of our standard model of cosmology, lambda CDM. And what we find by doing that measurement approach is still in agreement with the power spectrum approach from CMB measurements. You can see that here. I'm just going to flash these slides up. The TLDR here is that we're doing better than we ever have been by combining different data sets in terms of measuring cosmological parameters. And we're in good agreement still with satellite measurements of the CMB. Here again, you see a really pretty map of peaks and voids in this dark matter map distribution. And what's neat is you can overlay it with the Planck CIB, so basically looking at where dust is, where dusty star-forming galaxies live. And those contours are overlapping the peaks and voids, now shown in white and black. And you can see how well they agree just by eye. Right? So dusty star-forming galaxies live where the matter is, which is kind of natural, but now we can show that in a really beautiful way. Okay, now I've nodded to the increased resolution of ACT over other experiments like Planck because of this large mirror, and now you'll get to see that kind of side by side. So this is a map of the Planck measurement at 150 gigahertz of the cosmic microwave background. To give you some scale, these boxes are 2 degrees by 2 degrees. And now I'm going to flip between this and the ACT measurement. So this is now adding in ACT data to the Planck data. And you should see that increase in resolution just right before your eyes. And what you're also seeing is some astrophysical sources begin to pop out of the ether here, especially over here, I think. These big ones arise. And so these are radio and infrared point sources. There are also something else in this map. They're not red points. Does anybody else know what I'm about to say next? I'm going to get into Sinayev-Zlodovich effect land to give you a hint. You can see galaxy clusters. Whole galaxy clusters. They're just very kind of faint, but here are some circled. These are blue dots at 150 gigahertz, and I'll explain why in a little bit. But I just think it's so fantastic that we can take this image and just see by eye some of the largest gravitationally bound structures in the universe. It's only using the ACT data that we're able to do that. If we go back to Planck, like look up here, what is there? Nothing, and then it pops out. So the Sinayev-Zldovich effect is a very long and fancy name for what happens to CMB photons when they inverse Compton scatter off of electrons in the universe. These electrons are mainly in the gas that clusters into galaxy clusters, just because that's where the mass goes. And so the scattering event gives the photon a little bit extra energy. So in this video, you see it blue shifted. The additional energy takes the CMB blackbody spectrum and just shifts the whole thing up. And so you see a change where you're observing through a bunch of baryonic matter in the CMB. I'm going to freeze frame on that last part here. And you can note that this is a frequency-dependent effect. So in what frequency you're looking at, your signature is going to look very different. At 220 gigahertz, you actually see nothing at all. Below that, you see a decrement in temperature, and above that, you'd see an increment in temperature. And I like to show this picture to explain that. So you have the blackbody spectrum of the CMB natively in blue, put it through, in this case, a very exaggeratedly large cluster mass, and the whole spectrum shifts up, which means that if you observe at 220 gigahertz, there's no change, actually. Below that, there's a decrement, above, an increment. And what this signature is telling you is the number of CMB photon scatterings you have times the energy gain per scattering event. It gives you a tool to illuminate the baryonic matter in the universe by scattering events from the CMB as they go through the matter before reaching us at Earth. So it's kind of like the gravitational potential thing, except now it's an electromagnetic interaction. And the signature you observe, the temperature signature in the CMB that we just looked at, is proportional to this Compton Y parameter that gives you a physics measurement of what's happening to the CMB photons. And so you can use this as a tool in two different ways. You can just take your CMB map and be like, oh, hey, here are galaxy clusters, which is what we did with our eyes just some slides back. Here, though, you're applying a matched filter. You're increasing your odds of seeing one of these, but you're still signal-to-noise limited, meaning if the galaxy cluster is not massive enough, based on the sensitivity of your survey, you're still not going to catch it in the map. There are other less massive bodies, like gravitationally bound groups, that aren't shown in the map. But we have worked on cataloging these galaxy clusters using these surveys, and we've done so to great success. So the first maps made, we had a couple hundred. Now we have over 4,000 galaxy clusters that can then be follow-upped with optical measurements to say, yes, that is a galaxy cluster. So we have follow-up measurements, and we're doing astrophysics using the cataloged clusters from our millimeter wave surveys. But also, we have surveys like the Sloan Digital Sky Survey shown here that are really, really good at measuring where galaxies live. And galaxies often live in these gravitationally bound groups and clusters. So we can use the optical surveys to tell us where to look in our CMB map and then give us a statistical approach to measuring these objects as well. Here are just some more images of what this looks like. When you are mapping in the millimeter wavelengths, you can see now a number of frequencies on the left-hand side, different data sets across in the columns, where the leftmost column is Planck, then you have the ACT and Planck coad, and ACT alone on the far side. In 220 gigahertz, you'll again notice those galaxy clusters just kind of disappear. So measuring the SZ effect gives you a tool set to identify clusters, to measure their statistical properties, but it also allows us to map across the whole sky the baryonic mass at large. And that's what you're looking at here. This is Compton Y measured over about a third of the entire sky. And if you take a look at this paper and zoom in, it's really very beautiful. You can just go into this kind of fiery map and see in a new way, you know, these both of the objects that I mentioned and also just where the mass is. So we know that baryons are extended in ways that are a little bit more beyond what we would naively expect if we just assumed dark matter halo models of these objects. And so you can see some of that diffuse baryonic matter. And indeed, we're trying to do that better in order to understand how objects like galaxy clusters formed over time, which we still do not have a great understanding of. We have to assume a lot of subgrid physics in our simulations that we can really improve by making better measurements of Compton Y. There's also this second type of SE effect that I just want to nod to and then tell you a little bit about why we're excited about it. So the kinetic SE effect is again a shift in the CMB photons, but instead of being due to the temperature of the electrons in the hot cluster gas, it's due to the way the clusters are moving in the large-scale structure of our universe. So it's a Doppler shift of CMB photons due to the bulk motion of the gas. And what's really neat is that the way that galaxy clusters are moving around in our universe directly probes the large-scale structure as it evolved over cosmic time. So you're watching these things move around, interact gravitationally, and then you can use that as a probe for dark energy, for models of modified gravity, and for fundamental particle physics like neutrino mass. So in this diagram, you see the way that photons will scatter with electrons that have some velocity relative to our line of sight. And so if a galaxy is moving towards us along that line of sight, you get a blue shift in the photon. If the galaxy is moving away from us along the line of sight, you get a red shift. And so then you can do some statistical measurements, which I won't get into the details of, in order to both measure the optical depth of the cluster gas, which is interesting for astrophysics, and also the velocity of the cluster gas, which is interesting for cosmology. Here in the simulation, you can see what large-scale structure would look like without any mass in neutrinos, or with some exaggerated amount of mass in neutrinos. And you can note that neutrino mass directly impacts large-scale structure. So neutrinos act as little mass bandits. They take the mass of the universe and kind of run away with it. They don't want to cluster down into these gravitational wells because they're free streaming relativistically at early times in the universe. So you see a smearing out or a washing out of the overdensities of the large-scale structure. And then the velocities of the clusters as they move around in those gravitational potential wells are impacted by this. So our velocity plot, so y-axis velocity, x-axis is the separation distance of pairs of galaxies. It's a statistical method of looking at relative velocities. But those relative velocities will change as the large-scale structure changes, giving us a toolkit to constrain the neutrino mass sum in the universe. Otherwise, inform us how much of the universe's mass could live in neutrinos. This is exciting because we're using the universe now as a lab for fundamental particle physics in a way that's highly complementary with other experiments happening on Earth. And they can tell us interesting things like what happened perhaps with this whole matter-antimatter asymmetry situation. Do you all know about that? There's this very small imbalance in matter versus antimatter, which allows us as matter to be here today, having this chat. Otherwise, we would just all annihilate into energy. Nobody knows yet why this small asymmetry occurred early on in the universe's history, and one of those options is the type of particle that a neutrino is. So by studying neutrino mass, we can actually input into trying to figure out what neutrinos are, and if the way that these particles interact could explain this matter-antimatter asymmetry. We also, in the pie chart of the universe, this is my favorite pie chart to show, we know that the most of the universe is meringue. Dark energy provides this accelerating expansion in the universe that is an ongoing mystery in our understanding of physics. And dark energy, as well as these growth index descriptions using general relativity, tell you how structure forms over time. So I didn't make this. Everybody likes to ask me about how this is done. This is a really beautiful simulation of evolving forward, a mass distribution in the universe under the effects of gravity over time, as denoted here by redshift. And if you tune these parameters, tune the way dark energy behaves, tune the way general relativity behaves, you'll, of course, change the simulation. And the velocity of galaxy clusters, again, is sensitive to those changes. So if we're able to very carefully measure the velocity of these structures, we can start to place constraints on these very interesting values. We're also interested in astrophysics. So one person's garbage is another person's interesting signature. So for primary anisotropy science, you want to remove these signatures. For astrophysics, you want to study them directly. And so I have been stacking these, for example, averaging these together. This is a sample of 23,000 luminous red galaxy tracers that show you the average galaxy cluster profile of the gas in the structures that you wouldn't be able to notice just by looking at the millimeter wavelength maps alone. You need a cross-correlation with optical surveys. So what this can tell you is where the gas lives. You can start to study the baryonic distribution within these structures. You can learn about halothermodynamics. You can learn about feedback, non-thermal pressure, and serve as an input into the measurements of those velocities which is currently, we're actually limited by understanding what is going on with these structures. We can't measure velocity really carefully until we fully understand that. So this is where my work is in right now. We are actively trying to better constrain our baryon content of our structures, the profiles, the gas, the dust contribution to this that needs to be removed from this signature so that we can better understand how to make velocity measurements. So some previous work we did, make sure I have enough time for instruments here, was to overlap this longitudinal sky survey areas, which you can see in orange and green and blue, with one of our maps from ACT. And that gave us about 340,000 luminous red galaxies to work with. What's exciting right now is that we're working with a catalog of over 2 million from DESI, so we're going to improve this quite a lot very soon. But what we were able to do is make the highest significance detection of the pairwise kinetic SZ effect yet. This is exciting. It's not yet a measurement of velocity, so we can't do cosmology, but we're getting there. And it's not super important to understand all the details here, but just know that this minimum that we're measuring is a consequence of galaxies that are close to one another, moving towards one another because of gravity. So we're able to see that, and it sounds kind of obvious, like, yeah, we know that objects that are close to one another are going to be moving towards one another, but this is such a faint signal that we haven't gotten a 5 sigma measurement until this result. The community has been working on making this measurement for a very long time, since before I was in the field at all. So it's exciting that we're finally there. And now I'm asking, well, okay, I really want this plot, right? We want the neutrino physics, we want the cosmology. To get there, we're going to need to improve, you see these envelopes of uncertainties, we're going to need to make that much better. So we're on the road to that now with our improved statistics and our new methodology using the thermal SE effect to tell us about the structures. And this is just a preliminary hype slide, but I think it's really, this is now 400,000, it's better now. So we have another enhanced DESI catalog we're working with that again has over 2 million galaxies. So please stay tuned for this, we're really excited. Okay, so now switching gears to upcoming surveys, but I'd love if there's any question now that's hot in somebody's mind that they want to ask about the SE effects. Yes? That could be, but our current physical model doesn't allow for that. So when you add in things like that, then it changes the other parameters. But we see great concordance in the other parameters. So it's kind of it's a sticky math situation where if you change one thing to make a great explanation like that, it should throw things out of whack that we don't see out of whack. So people are actively trying to correct the equations and like make everything balance. But I mean, that's one of the great hypotheses we can try to investigate. Okay, I'm excited to talk to you about telescopes. I'm just going to use some terminology that may or may not be similar to what people are familiar with other wavelength regimes, so I'm just going to run through it. This is more important for people who are not at an astronomy meeting, but if I talk at physics departments, people are actually, this is helpful. So telescopes, get light into your camera. Here's just a little diagram. The light bounces around and hits our camera, but we call these cryogenic receivers. They receive light from the telescope, but this is the camera. We can take them in and out of our telescopes. They're cryogenic because we need to cool the detectors. So inside of these cameras, we see a bunch of structures that are all designed to provide mechanical supports and also cryogenic cooling of the critical elements that make up the detector arrays, including the superconducting materials, which I'll touch on in a little bit. Okay, I'll touch on right now. These are the detector arrays. I can't get into detector physics. What a neat part of the field, though. Like, we can do fundamental material science to make these new technologies that depend on novel superconductors that are multi-layered and have complicated edge effects and are pretty poorly understood, except that we know that they work really well for our detectors, which is a very interesting physics question, which you can then kind of run off with in a condensed matter direction if you're so inclined. There are two main types used in our field. There are transition edge sensors, and then there are kinetic inductance detectors. Both of these need to be cooled to around 100 millikelvin, so incredibly cold. We need dilution refrigerators. We can't even use regular cryocoolers that get down to like 4 Kelvin because that's too hot for us. And then the details of these are quite complicated, but transition edge sensors are these tiny little pieces of superconducting material that act as very sensitive thermometers. And kinetic inductance detectors have this breaking of Cooper pair situation that is directly coupled to a output resonance frequency, which means they are actively already readout multiplexed, which means that it just simplifies our electronics. Transition edge sensors need to be attached to a whole nother series of devices called SQUIDs, superconducting quantum interference devices, that will read out our signals. So there's two different architectures. Both are very exciting. Both are being pushed to their limits, and both rely on superconducting materials that need to be cooled in these cryogenic receivers. Yes? Yes. 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 That is what is enabling our polarization sensitivity. They are essentially antennas here in these crosses that are at angles to one another. And here you can see the crosses at different angles in these arrays. The light hits that. It is coupled through waveguides before it hits these devices. And by measuring the intensity in the different directions, we can map out the polarization. Okay, so the Simons Observatory uses transition edge sensors, and we are currently deploying and just seeing first light now with an array of new telescopes. The site is on Saratoga in Chile. It's at about 5,200 meters in elevation, and first light has been achieved with both the small and the large aperture telescopes now. So here in the site, you can see the small aperture telescopes, or SATs, here. This was the site of ACT. If you remember from the cool video before, ACT is now another SAT. And here is the large aperture telescope, which you can see here. And this being raised into the large aperture telescope is we call it the LADR, the Large Aperture Telescope Receiver, not the most clever name in the world, but it is the largest millimeter wave camera ever built. And here you can see it being hoisted into the instrument space of the telescope. And then over here is a picture that was sent on our Slack channel when a team was out deploying a SAT. And the caption is, "We're here to install SAT MF1," that's the name of one of the telescopes, "on the platform and chew bubble gum, and we're all out of gum." So taking this very seriously. The small aperture telescopes have a 1/2 meter diameter, and they're designed to target early universe inflation. So here you can see one of them coming together in UC San Diego. A couple years ago. A surprising amount of our job is very much like construction. We deal with rigging. We deal with we have hard hats sometimes. There's cranes involved. We have to lift heavy things, but we're not particularly well qualified to do this, but we do it anyway. We do it fine. So here is my colleague Nick Golitsky, and he's looking at the guts of the camera. That's the dilution refrigerator that creates the cooling power at 100 millikelvin. And here it is. So this is the coldest plate that he's touching right now. It's not on, so he can touch it. When it's on, we have a vacuum chamber inside of the structure, and then the cold plate is coupled to the elements that cool the detectors inside of the camera. There it is. That's the mixing chamber. This is a dilution refrigerator inside view, so you can see where the cooling power takes place. This becomes the coldest known place in the universe when it's on. Colder than interstellar space, because the interstellar space is heated by the cosmic microwave background radiation, which is kind of cool. It's very cool. So these telescopes are designed to measure, if you remember, the polarization signature that I was kind of indicating, this tiny signature that we're trying to get at. That's what these telescopes are attempting to do. We're looking to constrain models of early universe inflation. Here's one in the field. I got to go out here last year and for the first time work at the site. I had done my entire PhD not knowing if I could work at the high site because I have asthma and it's such a high elevation. Some people have health issues, other people are just fine. And I was just fine after 10 years of working towards this. So it was very, very thrilling to be out here. You can climb up inside of here. Humans fit right in there to give you a sense of scale. It's very cold, and you have to install stuff inside. But this is finally observing now, and they look really beautiful at sunset. And there's just something about an Atacama Desert sunset that kind of makes all the hard work kind of disappear from your mind. And then here you can see the night sky over the mountain. This photo does not do it justice. There are astronomy tours in San Pedro for a reason. It's beautiful night sky viewing. If any of you have the chance to go either professionally or just for fun, I highly recommend it. It's a beautiful place. And then here you can see some first light results. This is some planet being mapped. I forgot which planet at this point. It's not going to be a great planet viewing experience. This is an instrument designed for wide field mapping of the CMB. Okay, switching gears to the large aperture telescope. This is a video that was taken as it was being put together in Germany. That's where the telescope manufacturer is located. And you can see in there is actually a mass model in red of this camera. So this telescope is another 6-meter aperture telescope, kind of like ACT, but it was made to increase the mapping speed of the telescope, and it gives us a really nice observing platform to quickly map the sky in our frequencies. And it is also giving us a much larger receiver cabin that enables us to push the limits on these cryogenic cameras. This one, again, is the biggest one ever designed, and it still doesn't fill the field of view of the camera. So we could put even more in there, and are excited to, as time goes on, potentially fill the field of view of these two cameras, or two telescopes that I'm talking about for Simons and CCAT, maybe with next generation receivers for an upcoming CMB experiment. This was great. I got to go to UPenn. I'm here in pink. I just snuck in, like I wasn't supposed to be here that week. I was not planning this, but it just so happened that the camera was delivered when I was there to learn about optics module metrology, which is a separate topic. But I got to be here when it was delivered. It's very exciting. I'm not sure how many of you are familiar with the UPenn campus in Philadelphia, but it's not the easiest place to drive an enormous truck into. So they kind of shut down the whole road and had this thing delivered to the high bay, and it was very exciting. And so now I also got to go see it when it's in the telescope. Here it is inside of the instrument space in the large aperture telescope. Here its front plate is open so you can see some of the optical openings of the optics tubes that fill up the actual camera part of the camera. And here is a team that went to go set this thing up in the telescope for the very first time. And it's thrilling that we finally saw first light last week. We were waiting on the mirrors to be delivered. Do I have pictures now? Pictures here. The mirrors were delayed in a terrible, this awful accident where the mirror panels were literally in the CAD software of the engineering company mirrored in such a way that they didn't fit. And so we had a year delay, and they had to remake half of the whole mirror panels. It was excruciating for the company. For us, it was, yeah. But finally, after a very long time, and I hope that engineer is doing okay after that, we got I would not want to be them. We got the mirror, we lowered it into the telescope. This was very exciting to watch on the live feed, see pictures on Slack, see the web camera. But then we saw this ridiculous day. Look at this weather. That's some of the worst weather that anybody has ever seen at this site. This is, again, 17,000 feet in elevation, driest desert on Earth. And it's in the fog. But they proceeded for some reason. I don't know exactly what choices they had, but they did lower one of the mirrors into the telescope in these conditions. It looks very metal. It was very exciting. All right, go back a few slides just to talk about what we're going to do with this thing. This large aperture telescope is going to give us access to the high resolution images. So small aperture telescopes go after polarization. Large aperture will go after the SZ effects, like I've talked about today. These small little structures that you can only resolve with these big telescopes. It's going to overlap with a large amount of optical surveys, so not just DESI, but also Roman and Rubin, and it's going to give us cross-correlation abilities with new experiments that are really going to open our eyes to, tenfolds or more increase in tracers for statistical methods to measure cosmology, astrophysics, fundamental particle physics. It's very exciting. So happy to have seen first light. Okay, switching gears to CCAT. So CCAT is going to field another copy of the LAT. It's going to look just the same, but the mirrors are better. The mirrors have tighter tolerances because we're fielding this at not just 17,000 feet, but over 18,000 feet in elevation. You can see the site from the previous ACT site, the Simons Observatory site. It's just up on the next mountain near Alma. The Alma Plateau is down below here someplace. And the higher elevation is going to cause us even more work problems where people aren't even allowed to work up there for a number of consecutive days. You have to come back down. You have to, there are all these extra procedures. The medical checkup that you need to pass in order to get up here is, there's one doctor who can do it in Santiago, and that's the only way. You put you in a pressurized chamber. There's this whole thing. So we're going to try to figure out how to actually get up here. But the reason we're up here is because it's the best site you can drive a truck to without going to space. And it puts us above even more of Earth's atmosphere so that we can push to higher frequency measurements. Now, okay, these pictures are getting less exciting now that we actually have the whole telescope in the site. So it's the same telescope as you saw before. And it's currently on a ship on its way to Chile. It should get there in about 2 weeks. And we're hoping to see first light early next year. So this is going to be the highest throughput submillimeter telescope ever built. It has this high surface accuracy and the same large field of view, same fast mapping speed, and it will serve as a potential platform again for the next generation experiment because we're at an even more uniquely equipped experiment site for high frequency measurements. Here's a map of what I just told you. The Alamo Plateau is down here. Simons Observatory is on Cerro Toco, and CCAT will be on Cerro Chachantor. Here's the site as it was under construction. It's much farther along now. The road is finalized. This is the foundation for the telescope being poured. And this is a nice chance to contextualize the site in Chile. Chile is a very, very long country. So we have colleagues who are down in the south working on Rubin, for example. And it's so tempting to be like, oh, I'll be in Chile. Like, we should meet up. And it's a long way away. You can't just meet up. But we're in the north, right on the border of Bolivia. This is the ship. It's the Sloman Discoverer. That's what's carrying our telescope right now. And this was a previous update. It was on a Caribbean cruise vacation at this moment. Now it's passed through the Panama Canal and it's going down to South America. So PrimeCam, again, this is such a great time to be giving this talk. I was giving this talk, a year or two ago, and it's like, it'll be coming. Now PrimeCam is actually delivered to the lab at Cornell, currently being integrated right this moment. It was delivered February 18th. So, I mean, this is all just finally happening after many years of work. I was working on this through my PhD starting in 2017. So getting my hands on the instrument is going to be fantastic. PrimeCam is basically a smaller version of the Large Aperture Telescope receiver for the Simons Observatory. It's 1.8 meters in diameter. You can still, if you're my size, just kind of walk into the thing. It will hold up to 7 instrument modules. These are kind of I keep calling them camera guts. They are modules that contain lenses and filters and detectors. You can take them in and out. And we've made them to be swappable between the Large Aperture Telescope receiver for Simons and PrimeCam, just to simplify our technology and have this modularity ability to customize instrument modules for various science goals. So once complete and fully populated, PrimeCam will be the largest scale deployment of kinetic inductance detectors for cosmology, for astronomy ever deployed. About 100,000 detectors. Like I mentioned, this is the only way to make better measurements right now. Our detectors are very good. They're actually as good as they can get. So we need more of them. This is one of our steps to deploying as many of them as we can. Yep, yeah, so there's an 80 Kelvin stage in the front for filters. There's a 40 Kelvin stage wrapping around the outside. And there's a 4 Kelvin stage in blue that will cool the outside of all of the tubes. And then finally, there's a dilution refrigerator in the back that cools to 1 Kelvin and ultimately the detectors to 100 millikelvin. So the science goals for PrimeCam are many. I cannot get into them all. But the great thing about CCAT is that it provides all of these complementary measurements for the cosmic microwave background, as well as the opportunity to do small field surveys, to do novel types of astronomy at submillimeter wavelengths. So not only are we going to be looking at CMB foregrounds across this wide area, studying galaxy cluster evolution by opening new windows at higher frequencies for SZ physics, also looking at potentially measuring Rayleigh scattering, which is this very interesting effect that happens in the CMB at early times. It's never been measured before. But also, we're looking at these smaller field surveys. We're going to be looking at the Milky Way, studying polarized magnetic fields, looking at galaxy evolution, dusty star-forming galaxies, and giving us tools for time domain science, watching how objects change over time in the sky. So it's an exciting suite of science. And if you're interested, this paper on the archive, our CCAT science goals and forecasts, will tell you more. Here you can see, I mean, it's a little bit intuitive that if you have telescopes observing from the same site in Chile, that you're going to have the same overlap on the sky, and indeed will overlap completely with the Simons Observatory Large Aperture Survey, as well as with these optical fields like DESI. SC Science is going to be exciting because here on the right, you can see the new frequency bands that CCAT is going to open up in blue. The blue bands give us higher frequency coverage because of the uniquely high elevation site. That will give us access to things like the relativistic SC effect, which creates a certain spectral dependence on the frequencies that we can only access by pushing to higher frequency coverage. So we're also going to be improving measurements of the cluster surveys themselves by constraining for systematics. I mentioned very briefly earlier dust contamination. That remains a very large concern, and we need to be able to directly measure the dust in order to properly model it and remove it from our objects. This will enable us to push from where we are right now in the orange colors to where we will be in blue at lower mass and higher redshift than ever before in SC cluster science. We're also actively developing these receivers. So this was me a few years ago in the lab at Cornell, where I was before I was at Duke, working with students to close up the shells of ModCam. ModCam is a small, single module cryogenic, it's not small, a single module cryogenic receiver that will test single modules for PrimeCam. It could also test modules for Simons. And it gives us the ability to quickly cryogenically cycle these things. It takes a long time to cool down and warm up your large camera. So this will have fast turnaround. And also, PrimeCam isn't ready yet. So ModCam will be ready. And we'll see first light on the CCAT telescope in 2026. By the way, I don't think I called it out, but FEAST, the acronym stands for the Fred Young Submillimeter Telescope. This is the name that was given to the CCAT Observatory's first telescope. So it's kind of the same thing as the CCAT Observatory Telescope, but named for our generous donor, Fred Young. So that's in process. We are now seeing optical tests for the first time. So I got to visit Cornell, finally, go into the lab, wave my hand in front of the instrument, and see the pickup on the detectors. It was fantastic. So we're testing our module. This is the first 280 gigahertz module. I love these pictures because it kind of looks like a fish, right? Like we went fishing and we're like, we got the big fish. But it was a very, very long in the making fish. We install this into the camera with these really fun counterbalance weights with weight plates from Amazon. So you kind of have like your home gym, but in the lab. And so inside of this thing are lenses, filters, custom metamaterial tiles for blackening, a whole bunch of structures that I'm happy to talk more about in detail another time. Ultimately, the light will get onto our detector array that's back here, and the signals are read out the back of this tube. And so here you can see some images of the detector array. This is work led by many, many talented people, but Cody Duell, who's currently a postdoc at Cornell, has been doing a lot with this. Yeah. So the lens material for all of our frequency coverage is silicon. We use silicon with anti-reflection coatings that are metamaterial etched onto the surface of the silicon. Yeah, silicon provides us nice cryogenic properties. It is delicate. We can't drop a screwdriver on it or anything, but it gives us a nice optical performance and good cryogenic performance at our frequencies across the bands from 20 to almost 1,000 gigahertz. Couple inches at their max. I don't know the answer to that. Yeah. Yes, it does. It does give a great. So any attenuation of like any band pass definition is coming from our filters, not the silicon. This is us putting the module in for the first time with that counterbalance with the weights. So we've done a series of cryogenic tests, dark cryogenic tests, and finally now we have optical tests with the window open to the room. We've done some cold load measurements. We've done now beam characterization, and so work is actively ongoing to pass our instrument readiness review and ship this to the site hopefully later this year. It's 2025 right now, so yeah, later this year. So we're going to see first light next year. Just some more smiling faces. Excited to do early science with this module. So there's a bunch we can do as soon as this is on the sky. We're going to pursue an early science program with ModCam on Feast for characterizing foregrounds, for characterizing the atmosphere. We've never observed from this site before. It's going to be very interesting to see how the atmosphere looks for the first time. We can go after a suite of PrimeCam goals as well with this one frequency band. And then a number of other modules are currently underway for PrimeCam that will test in PrimeCam at Cornell very soon. Okay, this is my summary. A lot of stuff is happening. It's very exciting. Hopefully you're excited too. We have new telescopes, new cameras coming online right now, improving our sensitivity, our resolution, our frequency coverage. We're going to be constraining the physics of our universe. We've already yielded the best H0 measurements yet, and we're going to improve them further with SO, leading to potentially an even greater Hubble tension or maybe an amelioration. We'll see. We're going to be probing astrophysics with optical surveys in concert with our millimeter wavelength, in concert with our CCAT observations at submillimeter wavelengths. And these new windows are going to be getting us ready for the next generation of measurements as well. So the field is actively working towards preparing for CMB stage 4, always looking ahead to see what we can do in terms of technology development, analysis techniques, to really open our eyes of humanity, not to get too grand, but truly start answering these questions of what is in the universe and where is it all going. So thank you very much for your time, and I'm excited to talk with you more.
Questions for the
Yes.
video?
Yes, thank you.
There's an enormous investment in scientific equipment in Chile, and the politics is a little touchy. I take it that the scientists expect that the Chilean government is going to be nice to them in the long term. Would you like to comment on anything?
Yes. So. Right, yes, so these are great questions pertaining to the current political landscape of the science funding and the Chilean government, and the question about the manufacturing facility that is currently proposed for being near some of these unique observational sites. To answer your first one, I mean, gosh, there's a lot of uncertainty, right? We don't know. The hard part is that there is no real guidance in terms of what's going to happen with our funding. I can't speak to what's going to happen with the funding. Right now, we've been told to continue all efforts. We'll have to see where the governments go. I don't think that there's anything right now, any talk of there being risks with it. And I am not, just for the record, for the recording that's happening right now, I am not in any type of political arrangement with anybody. I haven't heard that the Chilean government is feeling one way or another about allowing partnerships in these observatories at these sites. There's a rich history in terms of observation at these sites in Chile. It's good for them in some ways. It's good for us. We've had great partnerships with the Chilean governments and local people. So fingers crossed that's not going to be an issue. The issue will be like grant funding. Can the scientists operate? Right now, we do have very generous donors. Both the Simons Foundation has been absolutely critical in setting up the Simons Observatory, and now we are on an NSF-funded project for advanced Simons Observatory. So the funding situation for Simons is pretty good. CCAT also, through Fred Young, other donors, is seeing a lot of support in addition to our NSF grants. And then stage 4 is really I think the biggest question mark of next generation funding. My perspective is that there will be a next generation effort. It's just, what is it going to be? I don't know. It's up to funding institutions, priorities, current administration. Well, most of their site team are Chilean natives who live and work in the cities and make this all happen. There's also kind of a rich network of people who are supplying housing and food, and everything is happening there. The instruments themselves are built and brought in, but the rest is home in Chile. And second question was, I'm forgetting, the construction. So I know that there's that petition that I signed, and if that's still available, I encourage you all to sign the petition saying that dark skies are critical. I don't know what the status is beyond that there's a petition for having it relocated. Yeah, there's a lot going on in the current climate. It's been overwhelming, to say the least. Yeah, so all of the different components are in different places. Detectors, primarily fabricated for CNCAT at NIST in Boulder, the National Institute for Standards and Technology. For the Simons Observatory, it was a combination of NIST and LBNL out in Berkeley. For CMB Stage 4, Fermilab and Argonne are doing a bunch of detector development. Primarily, national labs are doing the development. It's very hard to make these in-house. And so the rest of the electronics for readout and things like that come from various efforts, both in-house at university labs for characterization of thermometry, for installation of like extension wires, and also things like the readout harness, which you can kind of see in this picture right here. It contains strip line and custom elements that couple to custom readout electronics, and those are developed at the Arizona State University lab that does various types of RF readout development for a number of experiments. So it's really a multi-institutional effort. Yes?
The galaxies, stars, and other matter emit microwaves and strange frequencies.
So the question is, do astronomical objects emit in microwave wavelengths that we're studying? The answer is yes, especially dust contamination. So we are definitely seeing emission that we need to control for in order to see various signatures that we're interested in. Radio point sources are those bright red spots that you saw show up. We need to actively control for that emission in our measurements as well. All of these things tend to be at smaller scales than we're looking at. So for large scale physics, it's less important. For small scale, it becomes very important. Yes? Oh, yes. So, okay, the question is, what is the latest information on neutrino mass? You might have heard about this negative neutrino mass from DESI. I don't believe that there's negative neutrino mass. So this kind of goes back to the question about balancing equations, and like you can tune one thing to be funky and have something else pop out. So the situation with DESI's measurement of negative neutrino mass is that it's either that or a time evolving dark energy equation of state. So you can kind of pick your interesting new physics with that. New measurements from various experiments will get us a better answer. All the other experiments so far have given a sum of the neutrino masses that is not quite counting out one of the mass hierarchies of neutrinos, but getting there. So we are drilling down on, this much mass can be neutrinos, now it's this much, now it's this much, as in terms of an upper limit. I'd say the general consensus right now is that there is some amount of mass in neutrinos that is consistent with our 3-neutrino model in our new extended standard model of particle physics, with a mass threshold that doesn't yet, but nearly counts out one of the hierarchies, meaning neutrino states having different orders of mass. But the DESI result of negative neutrino mass is an interesting result that warrants future study. So we can't say anything definitive right now. It's all limits and equation balancing, and we'll learn more with these upcoming experiments. Well, that's the thing. That's why it plugs into your dark energy equation of state. Yeah, it remains to be seen.
In the millimeter, sub-millimeter range and stuff, are you able to observe 24 hours a day, or are you restricted by VR and optical?
Yes, great question. So the question was, can we observe 24 hours a day in millimeter? And yes, we can. But there are a bunch of systematics that come into play that make that a little trickier. For example, just the sun heats up our mirrors. Our mirrors are chunks of aluminum, as you saw, which is another difference with optical, right? You see in the mirrors, and they look pretty funny. They work very well in millimeter wavelengths, but there are effects from the day-night cycle that need to be taken into account. So it happens that when we are doing our analysis, the best data is still at night, and that's just because of systematics, not because of the sun being up. We also are limited in terms of we need to do calibration techniques on the telescope. Sometimes weather gets in the way. It's never that foggy, but sometimes it snows. Things happen where the telescope itself is literally covered with things, and you need to get it off. So like there are issues that come up, but it's not like we have to wait for the sun to go down to observe. We're trying to observe as much as we can. Yeah, so the question was, how do the new arrays of satellites impact this science? The good thing about CMB science is that we're mapping, continuously integrating over the same signatures over and over and over again. So it's not an immediate threat to the science because of the wide field coverage. It's a threat to transient science, for sure, because we're constantly seeing transient now satellites all the time. Once we start to drill down on some systematics limitations, it will become of greater and greater importance, and that balance will be pushed, right? So the better our measurements get, the more it matters, and the more time that goes by, the more satellites we're going to see, and it's tricky. So if you go to any of these astronomy conferences right now, there are professional organizations that are trying to unite the field, and I have a number of colleagues who are actively involved in that, trying to advocate for dark skies, and there are a number of efforts to try to control for that. Some are limiting where the satellites go, especially with respect to these unique sites in Chile. Others are trying to design the satellite coatings, the satellite emissions, the band politics. There's so much band politics that I didn't know about that I'm just starting to learn about. So there are efforts underway to try to mitigate it. It's not immediately going to shut down our science programs, but it is something to constantly work on.